So Unit 1, final exam review here. Okay, so we'll look at all the important things for kinematics. Okay, and I'll talk about the important concepts, and we'll go over some examples of the types of things that are going to be on the final exam for this unit. All right, so the first thing we went over, scalars and vectors. Okay, and that's something that goes through for every unit. Okay, knowing what quantities are scalar quantities, what quantities are vector quantities is important. Okay, because you need to know when to apply certain, vector addition rules, or when an answer needs a vector and when it doesn't. Okay, things like that. So what were some things that we went over that were scalar quantities?
Speed.
Speed is a scalar quantity. Distance is a scalar quantity. Time is a scalar quantity. Work and its counterpart, energy, okay, are scalar quantities for sure. Okay, also things like period and frequency and stuff like that are obviously scalar. Okay.
What about gravity? That would be vector, right?
That's vector because it's acceleration, and any acceleration is a vector quantity. Okay, so acceleration is a vector quantity. What else? Velocity. Displacement.
I was going to say displacement.
That's good. Those are the big ones. Okay, so if we're looking at this here, acceleration, displacement, velocity, time, distance, speed, those are the ones for this unit, but obviously we talked about work and energy also being scalar quantities. Okay, then we talked about V equals d over t, and its counterpart, V equals d over t. Okay, one of them being speed equals distance over time, the scalar version of that formula, and one being velocity equals displacement divided by time, which is also sometimes written like it is here on the right. Final position, okay, final position minus initial position, okay, divided by time. Remember that displacement is your change in position. There's not necessarily going to be any big problem-solving questions to do with V equals d over t, because, well, that's beneath you at this point. Okay, I'm not going to waste questions on that. But it could be part of a graphing question, say in a multiple choice situation. Okay, or it could be part of a multiple choice question where I simply decide, this is worth 1 mark. Here's a simple, description of a trip where it could be a vector or a scalar situation. I think the one on your unit exam was something like it. Somebody leaves the classroom and they walk 10 meters north to the bathroom, and then they go 20 meters south to their next class. What's their distance traveled? Okay, well, they went 10 and then they went 20, so their distance traveled is 30. Okay, but their displacement is actually only 20 south. Okay, because I don't know if I remember if I put north or south, but whatever. Okay, it could be something like that. Okay, where you have to remember, oh right, distance is scalar and displacement is vector. It's a simple calculation. It's worth 1 mark. Okay, so it could be something like that. Okay, but it's certainly going to be on there. And the other place where this comes in, projectile motion. Okay, for the horizontal component of projectile motion, because it's constant velocity, right? There's nothing to accelerate the horizontal component of a projectile, because we do this in a vacuum where there's no air resistance. Okay, so it could be part of that as well. So it's something you need to know how to use. It's not a difficult thing to use, but it's definitely on there. Okay, then we talked about graphing. Graphing is a big part. Okay, there's some graphing questions on your final exam. Both multiple choice and I believe I put one in the written as well. Okay. So definitely be able to use your y equals mx plus b. Okay, because there could be some of that. Okay, give you a graph and give you the equation for the line and ask you to use it to calculate things. I did that on your unit exam. Okay. Or just being able to do certain things with your graph. Okay, so if it's a position versus time graph, okay, then my y-intercept, or b, would be my initial position, my position in time 0, okay, and then I could be calculating a final position. X is obviously the time. What does the slope represent on this graph? Velocity, okay, and here's why. If I manipulate that for slope, I've got y minus b over x, which is final position minus initial position divided by time. Okay, those are the things that we have to be able to either figure out on the fly or we just remember. Okay? But it's certainly an important skill, okay, for using graphs. Right, so that would be for, oh, I already had it there. Okay, and then we've got our velocity versus time graphs, okay, same idea. The slope of the line on there is going to be our acceleration, because that's what y minus b over x translates to on this graph, is final velocity minus initial velocity divided by time. Okay, you could be asked to calculate displacements, okay, and you had to do that on your acceleration lab. And that involved a calculation that was kind of like this. Okay, where I gave you, or you had made the graphs, okay, that were linear, and you just had to calculate the displacement, which meant you calculated the area of the rectangle and the area of the triangle. Okay, the area of the rectangle was d equals average velocity times time, and so was the triangle. It's just that the velocity was changing, so we had to go the height of the triangle over 2 to get our average, because our average would be halfway from bottom to top. Okay, and so the same idea works for that. Okay, and then you just add them up. Okay, is that ringing a bell? All right, so certainly there'll be some graphing, okay, to do with that. And if I had an irregular graph like this one, then I would have to find the area of all of the shapes. Okay, so there'd be like a rectangle right here, there'd be a triangle right here, and then there'd be a big rectangle right here. Okay, or I might give you a graph like this in a multiple choice question and say, what kind of motion is happening in section A? And that would be like A, constant velocity, B, negative acceleration, C, positive acceleration, or D, not moving. What would it be? C, positive acceleration. This thing's velocity is becoming more positive over time. Okay. All right, is that ringing a bell? And then we talked about acceleration. Okay, we've got all kinds of acceleration formulas on our formula sheet. Incidentally, you're getting exactly the same formula sheet, just a fresh copy of it for your final exam. Expect that there's likely going to be some acceleration problem solving, especially since it's part of projectile motion. Okay, and we had to use most of our acceleration formulas in projectile motion, depending on which, on the question, what both we were given and what we had to calculate. Okay, so there could be, simple problem solving in the multiple choice part for an acceleration question, and it's definitely part of projectile motion. And spoiler alert, there's a projectile motion question on the final exam. It's the first question in the written response. That's a picture of Mr. Dickey acting really, really cool. You'll see it when you get there. Okay, so that's what we'd be looking at there. Vector addition, is that going to be big? We had to do it in Unit 1, and we had to do it again in Unit 2 when we were trying to find the net force, okay, the vector sum of all the forces. So definitely know how to do that. How do we draw vector quantities? Tail to head, okay? And it's like you're telling a story, draw it in order. Okay, first they did this, and then they did this, and then they did that. Okay, draw them tail to head. Okay, then you got to find their x and y components, and then you got to add the x's together and the y's together and get the overall picture. Okay, I would say there's definitely going to be some vector addition on the test. Okay, so you know what? Just for the sake of practice, try this one. See if we can still do it. Okay, so we want to add those vectors. 10 meters at 30 degrees north of west and 12 meters south. All right, I'll give you guys a couple of minutes. Let's say I'll give you 5 minutes. Okay, I think you should be able to do it. Maybe 8, between 5 and 8 minutes. Hey, Mr. Schmidt, 5 to 8 minutes, please. All right, so the first thing we want to do for this one, and I'm going to shortcut and cheat because I had it already done, okay, is we want to draw our vector diagram. Okay, so we draw it tail to head. We draw first that 10-meter vector, okay, which you see in black here. So I draw this line, right, and then I draw its x and y components. Okay, so that's this line here and this line here, and then I draw the 12 meter south vector. Scale is important. Okay, I drew the 12 meter one longer than the 10 meter one, and it's due south, so it's the red line here. That means my resultant goes here, the green line. Okay, and my resultant has a southerly directed y component and a westerly directed x component. All right, now that I've got that step done, I need to find the x and y components of my two vectors. So for the black 10 meter vector, my x component here is the adjacent side, so I'll use the cos of 30 times 10, which comes out to 8.66 meters west. I will use sine because the y is the opposite side, okay, and it's north, so sine of 30 times 10 is 5 meters north. All right, so I've got the x and y components of that. The 12 meter vector is easier because it's not a triangle, it's straight south. Its x component is going to be 0 because it doesn't go east or west, and its y component will be 12 meters south because that's all it does. Ring the bell so far? Okay, then I take those vectors and I add them together to get my resultant vectors, ry and rx. So for rx, okay, it's going to be 8.66 meters west because that's the only one that went west. Okay, and for my y, I'm going to have 12 south minus 5 north to give me 7 meters south. All right, so my ry here is going to be 7 meters south, that one there, and this one here is 8.66 meters west. Okay, now I can take those and get the magnitude of my overall displacement. Okay, so I do Pythagorean theorem, 8.66 squared plus 7 squared, and of course I would keep all the decimals for that 8.66. Okay, so when I do that, I'm going to get that I get 11 meters, or 11.135 meters. Then I've got to find my angle, okay, my resultant angle. That'll be this one right here. Or, okay, it could be this one. It depends which way you drew the triangle. For me, it's going to be this one. Right? And I'm going to go opposite side, which was the 8.66, divided by the adjacent side, which is 7. And when I do that, I get 51.05 degrees west of south. Now I combine that, I only have two significant digits, so I have 11 meters at 51 degrees west of south, okay, but I could also accept 39 degrees south of west, okay, as another vector for that. All right, ringing a bell? Okay, now the finding of the vector components, that was finding x and finding y, that's also a part of projectile motion. Okay, so we definitely need to be able to find x and y components, okay, because finding the y component on a projectile motion question gave us our initial velocity, finding the x component gave us our constant horizontal velocity, okay, for that type of question. So important that we know how to do that for this one. Okay, then projectile motion after that. Okay, there's two kinds of projectile motion. Projected at an angle, okay, the examples we did, really, drive off a cliff, or something like that, okay, run off a diving board, whatever, you're not moving vertically at time 0, okay, and then the other kind we went over were projected at an angle. We looked at, lots of jump scenes in movies, where they're jumping cars over things and stuff like that, okay, those would be prime examples of projected at an angle, projectile motion problems. Okay. Which one do you suppose I'm going to put on the final? Projected at an angle. Yeah. Okay. And the reason I'm doing that is because it tests a whole bunch of things with one question. It tests, can you do v equals d over t? It tests, can you find vector components? It tests, can you do an acceleration problem? Okay. It does all of those things in one question. So it makes the exam shorter. See, it's good for you. Yeah, it's good for me because it's less work. Okay. So it works out both. Right? So definitely expect to get the projectile motion question on there. Okay, so if we had one like this is one of the horizontally projected ones. Okay, the big thing to remember about those is that at time 0, I'm not moving vertically. Okay, just in case there's a multiple choice question around this type of projectile motion, which is entirely possible. Okay. So in a situation like this one here, we're told how far it hits the ground, and we're told the speed it goes off at, and we would have to work backwards. So we have to find our time, which we could then use for the vertical part, because time is the one thing we can use in both types of projectile motion for both horizontal and vertical parts. Okay, so make sure that you remember how those work, and then okay, so that's the finish of that one. let's try one. I'm sure I've got one here. All right. I'm just going to redo this. Pick some new numbers. And now we get a nice pretty color there. Okay. So all right, so here's our projectile launched at an angle question. The projectile is launched at 60 meters per second at an angle of 35 degrees above the horizontal. I want you to calculate for me two things. The total horizontal distance traveled, assuming its launch point and landing point are the same, they're level. Okay, so there's no change in height vertically. Okay, and the maximum height. Okay, so I want horizontal distance, and I want max height. Okay, let's see how much we remember there. Okay, I'll give you about 5 to 8 minutes for that. Okay, Mr. Schmidt, about 5 to 8 minutes, please. All right, so with an angled projectile motion question, okay, or with any projectile motion question, we still want to break this up into its vertical and horizontal parts. Okay, so what we know vertically, first off, is that the acceleration is negative 9.81 meters per second squared, or 9.81 meters per second squared down. Okay. We can calculate our initial vertical velocity because it will be this side of the triangle. Okay? Immediately after that, of course, it'll change because gravity will start to affect it. So we'll go sine of 35 degrees times 60. Whoops, sine of 35, brackets, times 60. Okay, it's 34.41. Of course, we're going to keep all the decimals, 34.41 meters per second, and that's positive. Okay, since I told you that the launch point and the impact point are the same height, what's VF? Nope. Negative 34.41 meters per second. What goes up must come down. Okay, and so by the time it gets back down, of course, in the perfect physical world, it'll be going exactly the same vertical speed it was when it was launched. Okay, everyone okay with that? All right. And then horizontally, I can calculate V horizontal. Okay, it's the adjacent side of that triangle. So that'll mean taking the cos of 35 and multiplying by 60 meters per second. Okay, so we got 49.15. Meters per second. Okay, so we've got that. That's not going to change. That's a constant velocity over there. All right, if I'm going to find the horizontal distance, what am I missing? Time. Okay, can I find that with the vertical information? Yes, I can. All right, so I'm going to use A equals VF minus VI over T because I have A and the two V's. I'm just going to manipulate for T. That'll be 34.41, negative 34.41 minus 34.41 divided by negative 9.81 meters per second. So in actual fact, all I need to do is take this number and multiply it by 2 and then divide by 9.81. All right, so this thing is going to be in the air for 7.02 seconds. All right, that I can bring over here, 7.02 seconds. And now I can calculate D because I know V and T. Okay, so I'll take my 49.15 and multiply it by 7.02. Of course, using all of the decimals I had before. Okay, it's going to travel, what do we have, 2 sig digs there, so 3.4 times 10 to the 2 meters. Okay, what changes if I want to calculate the maximum height?
Now VF is 0.
Now VF is 0, yes. Or time is half of what it was before. It depends which way you want to solve it. They're both equally valid. Okay, my preference on that is to use this formula here. VF squared equals VI squared plus 2AD, and just solve for D. Okay, so VF is 0, I subtract, so I'm going to have VF squared minus VI squared divided by 2A equals D. So 0 squared minus 34.41 squared divided by 2 times negative 9.81 gives me D. Okay, so I'm just going to take that 34 and square it, and then divide by 19.62. Okay, so the maximum height is going to be 60 meters. The other way that you could do this would be to use this formula. D equals VI times T plus 1/2 AT squared, but you have to remember to use half of the time we calculated previously. Okay, the benefit of this one is you don't have to manipulate anything. Okay, but you have to remember to divide the time by 2, and most people forget that when they use it. Okay, so if I do this, I'll have my 34.4 and my time, which was that number there. So I'm going to take that number and divide it by 2. Okay, and then I'm going to multiply it by that number. Okay, and then I'm going to add to that 0.5 times negative 9.81. That's another thing people forget with that one. Times that number squared. Okay, get exactly the same number as I should. Okay, just a different way of going about it. Either way is perfectly valid. All right. Questions on the projectile motion stuff? Okay. What else would you like to go over from this?
More projectile motion.
More projectile motion questions?
Boat questions?
A what?
A boat question?
A boat question. I'm not putting a boat question in the final. Does that help?
That does.
Okay. I mean, we could still go over a boat question if you wanted to, but I'm not putting a boat question on the final exam.
I'm sure.
How about we see if we can, well, first off, what's going on between 0 and 2 seconds on this graph? It's moving at a constant velocity of about 4 meters per second. Okay, what's going on between 2 and 5 seconds? It's accelerating positively. Okay, and then between 5 seconds and 7 seconds? Moves at a constant velocity of 10 meters per second, positive 10 meters per second in this case. And then what's going on in the last part?
It's accelerating negatively or slowing down.
Right, it's accelerating negatively. We could say it's slowing down, but it's only slowing down until what time? To 9 seconds. Okay, because at 9 seconds it's stopped, and then it's accelerating and increasing its velocity in a negative direction after that. Okay, so if I asked you on a test, like on a multiple choice question, describe the motion in the last part, it would be accelerating in a negative direction. Because if we say slowing down, that's actually only true until 9 seconds. And then after that, it's actually going faster, just in the negative direction. So always watch the wording, because if that was a multiple choice question, that would totally be one of the distractor items. Okay, slowing down would definitely be one of the distractor items. Everybody with me there? Okay. All right. Calculate the total displacement. And I'll make it a little easier for you. To 7 seconds. Okay, so you're only going this far. Okay, to 7 seconds. All right, give you like 2-3 minutes on that. Okay, Mr. Schmidt, 2 or 3 minutes, please. All right, so we've got, at least in the first part here, just an object traveling at a constant velocity, and then we've got an object accelerating for a short period after that. If we want to do this in the kind of smallest number of shapes possible, I would say we extend this straight to there, and then we would only have 3 shapes to do. Okay, up to you. As long as you get all of the area, you're good, but I would like to do as few shapes as possible. Okay. So when I'm looking at this, I'm going to have this area here, which is essentially saying it travels at a constant velocity of 4 meters per second for 5 seconds. So 4 times 5 is 20 meters. Okay, so that part's pretty straightforward. Okay, then I've got this triangle here that runs for 3 seconds on the base and goes from 4 to 10. Okay, so 3 times 6 is going to be 18 divided by 2 is 9 meters. And then I've got this last bit that runs from 5 to 7 seconds and is 10 tall, so that should be another 20 meter box. Did I read that okay? Good math. Okay, so we got a total of positive 49 meters. Okay, is the positive important if I ask for displacement? It's essential. Yeah. Okay. All right. Everyone okay with that one? Oh, there was a boat question. Look, somebody asked about a boat question. Okay, but we'll skip because I'm not putting boat question on there. No, that's a different unit entirely. Oh, and then we got dynamics after that. Okay, so what else would we like to go over? Another projectile you said, right? Okay, let's put another projectile motion.
Just a quick question, is there going to be a situation on the final where the final height is different from the initial height? Is there going to be a
No,
question?
because I didn't ask you to do that during the, well, I think we had one like that we did in class as an
Yeah.
example, but that's pretty involved for a final exam question. And that's not what I think final exams are about. Right? My philosophy is that's not the place to ask the hardest question. Right? What makes a final exam hard is the volume of material that's on it, not the level of difficulty of the individual questions. Not everybody agrees with me. I like to think of them as wrong. Okay, but yeah, it's certainly. I don't think that's what a final exam should be about. You should be able to demonstrate to me on a final that you still know how to do the stuff I taught you. Not, I can figure out the hardest question you could ever think of, even though I haven't done this stuff for 4 months. Okay, so let's look at another projectile question here, but I'll make it a little bit different. I don't think I've ever given you one like this. Okay, so launched at an unknown velocity. Okay, launched at an unknown velocity. I would like you to calculate 2 things. The horizontal distance and the projected velocity. Using only those 2 numbers. Okay, it's a little bit of working backwards, but it's a good exercise. I'll give you 5 to 8 minutes on that. Okay, so Mr. Schmidt, 5 to 8 minutes, please. Okay, so we don't get a lot of information here, and it's a much different data set than we would normally get. But because I know the vertical displacement is 20 meters, when the velocity is 0 meters per second, I can use that to get VI because I know what A is. And so I'm really working backwards in terms of the stuff that we've normally done with a projectile motion question. Sometimes it's a good exercise to do something like that. Okay, so I want to find VI. The formula I would use is this one. In fact, I have to because I don't know what the time is. Okay, and so I'm going to solve for VI. So I'm going to go VF squared minus 2AD equals equals VI. And I'm going to square root that. Okay, so I'm going to have the square root of 0 squared minus 2 times negative 9.81 times 20. Okay, and that will give me my initial vertical velocity. So square root of 0 minus 2 times negative 9.81 times 20. Okay, and the reason I put in the 0 there is because I put in a negative here. And if I don't do that, I'll get a negative number under the root, and my calculator will have a conniption bit because you can't take the square root of a negative number. All right, so VI, not the projected velocity. VI is 19.81 meters per second squared, or sorry, meters per second. So 19.81 meters per second, and that number is positive. Now from there, I can calculate what this number is because now I can use trig. I know what this side of that triangle is. It's 19.81 meters per second. Right, so if I want to get the hypotenuse using the opposite side, I'll take the sine of 40 degrees, okay, and I'll say it equals the opposite side divided by the hypotenuse, and I'll solve for the hypotenuse. Okay, so hypotenuse equals opposite side divided by the sine of 40. Okay, so that'll be the 19.81 divided by the sine of 40, and that'll get me my projected speed, which is something I'm going to need to do the second part of this. Okay, so I'm going to take that number and divide it by the sine of 40. All right, so the projected velocity is 30, we only have 2 sig digs here, so 31 meters per second. All right, I would say that would be the part A for this question. So do I use all those decimals when I'm calculating d horizontal? I do not, okay? I have to use this number now when I'm starting part B, okay? Nope, I carry my significant digits in. All right, so if I'm going to get d horizontal, I need v horizontal, okay? And to do that, I'm going to use this number here and this number, okay? So I'm going to go cos of 40 times 31. Okay, so that side is 23.747. Okay, now that I have that, okay, I still need the time. Oh, sorry, 23.74 meters per second. Okay, and now I'm going to find the time over here. Okay, going VF minus VI over A, knowing that I can use 19.81 for both of them. Okay, so I will do, oh, this would be a tricky one, sig dig wise. It would like depend on what order I do it in here. Okay, I didn't need the time for part A, but now I'm using full number values to calculate something. It's a tricky one. This is why you wouldn't get one on the final. There's just way too many out there kind of things to worry about. Okay, if it were me doing this, I would say because I did not calculate this in part A, I would be using full numbers to calculate the time. Okay, without rounding. Run with me on that. This was not a number I needed as a final answer. It was a number I calculated as an intermediate calculation. Thus, I would keep all of the decimals for that part. Okay, so I'm going to use that 19. Okay, 0.8 there to get the time, so I'm going to take that, multiply it by 2, and divide it by 9.81. Now I've got my time. I'm going to take that and multiply it by my horizontal velocity, and it's going to travel 96 meters horizontal. Right? So lots of reasons I wouldn't put one like that on the final. It's a lot of steps. Okay, we never did one like that in class. And it's got some weird sig dig stuff going on. Okay, stuff like situations we never really covered in class. All right. Okay, questions on that one? A little bit different anyway. Okay, any other questions you guys want to go over? vector addition. Okay. Let's make it a tricky one. Actually, let's do this. Let's make it a Newton's second law question with vectors. Then we're reviewing two things. I know we're not reviewing dynamics today, but okay. Oh, sorry, we need the mass of the sled. It's a 60 kilogram sled. Okay, there we go. Okay, so you got a sled, it's being pulled by two ropes. Imagine there's two ropes attached to the front of it. Okay, one of those ropes is being pulled 25 degrees north of west by 45 newtons worth of force. The other 70 degrees west of south by 52 newtons of force over frictionless ice, because that would just throw another monkey wrench in if we had that. Okay, so those are the two forces. It's like one of the least efficient ways I can think of pulling a sled, other than making them directly oppose each other. Okay, but that's what we got. So let's see if we can calculate that acceleration. But first, obviously, we have to draw the diagram, do the vector addition, and all of that kind of stuff. Okay. All right. So 10 minutes be enough? 45 newtons. It's 25 degrees north of west with 45 newtons of force. And then the other one is 70 degrees west of south by 52 newtons. Sorry, I know I use newtons and N for north. Okay, it's two different ends. Okay, all right, give you guys about 10 minutes. So Mr. Schmidt, about 10 minutes, please. I'm not going to solve the whole thing right yet. I'm just going to draw the diagram. Okay, so that we have it here. Okay, I know I didn't draw this to scale very well, but it's going to come out something like this. Okay, we're going to have our 45 newtons. Okay, that's going 25 degrees north of west, and then we're going to have our 52 that's at 70 degrees west of south. Okay, and I actually had to do the calculations on the calculator before I drew the diagram, because I wasn't sure whether the 52 was going to reach all the way back down. Okay, and either go past or end up short of my vertical starting reference. Okay, it ends up that it's a little bit short. Okay, we're a little bit above my starting reference point. Okay, but that's what our diagram should look like, with our resultant, which is the net force, being this line right here. So it's actually not terribly inefficient. We get a net force that's almost straight west, almost. Okay, so it works out pretty well there. This will be our resultant net force. This will be our angle. This will be our resultant y. Resultant x. This will be our resultant y over here. Okay, and then I'm just going to redraw this in a different color so we can tell them apart. so this will be x2, and this will be y2. And then we'll have x1 and y1. Alright, so that's what our diagram should look like. I'll give you another 2 minutes to kind of finish that one up. Okay, so if we're looking at this one here, okay, we're going to have x1, that's going to be, because it's the adjacent side, it's going to be the cos of 25 times 45 newtons, okay, and y1 will be the sine of 25 times 45, okay, and then x2 will be the will be the sine of 70 times 52, and y2 will be the cos of 70 times 52. Okay? The reason I'm writing them all down at the same time is because I calculated 2 of them already, okay, in order to figure out whether I need to put the way I need to draw the diagram. Okay, so xy1 comes out to 19.02 newtons north, okay, and y2 comes out to 17.79 newtons south. Then we're going to calculate the other two, so cos of 25 times 45 to get x is 40.78 newtons west. Okay, and the other one is the sine of 70 times 52. So we got 48.86 for that one. Newtons, and that one will also be west. Okay, so now that we've got our x and y components for both lines, we need to add them together to get our resultants x and our resultants y. So our resultants x is easy because they're both west. We just need to add them together. Okay, so that's going to mean taking that one and adding that one. Okay, so our resultant x is 89.65 meters. Okay, and our result y is going to be very small, okay, and it's going to be slightly north, so we're going to take the 19, that one there, and we're going to subtract the 17. Okay, so our resultant y is 1.23 newtons. Sorry, I said meters, but it's newtons. 1.23 newtons. Okay, this is west. This is north. Okay, now that I've got those, now I can calculate what my net force is using Pythagorean theorem. Right, so it'll be 89 squared plus 1.23 squared, which probably doesn't change it. Okay, but we'll see. So square root. Oh no! How do I go back?
Second click.
Second clear?
No, second mode. Second mode.
Second mode. Real lifesaver. Okay, so I want a square root sign. There we go. All right, and I want to take this squared and add it to that squared. Okay, so yeah, it changes it just ever so slightly to like 90. Sweet, okay. So we got 90 newtons as our net force. Then we need to find the vector for that. Okay, and so that'll be, I'm going to use 10 because I've got opposite and adjacent sides. So 10 to the minus 1 of the opposite side, 1.23, divided by the adjacent side, 89. Okay, but obviously I'll use all the decimals when I do that. So second 10 of that side divided by that side. Yeah, so less than 1 degree. It's almost perfectly west. Okay, so we would have 0.79 degrees north of west. Okay, for that one. Okay, Okay, so my final answer would be 90 newtons, sorry, that's not my final answer, 90 newtons at 0.79 degrees north and west, but I wanted the acceleration, so I actually need to take that force that I got, okay, that one there, and divide it by 60 kilograms, whoops, divided by 60 kilograms, okay, and I get 1.5 meters per second squared at 0.79 degrees north of west. All right? Everybody with me on that one? Okay. Could you get something like that on your final? I'm nodding yes. Yeah. Okay. You definitely could get something like that on your final. Okay. All right. So if you still got some time, obviously you can work on the final exam review that I put on Google Classroom on Friday. Okay, and that's what you should be working on if you've got time, like the 5 minutes that period 2 has right now. Okay, you could be doing that because we want to make efficient use of our time. And tomorrow we'll be doing a dynamics review. Okay, so we'll see how that's. Just be ready for dynamics. Then Wednesday, circular motion, and Thursday, general questions from you guys on all 4 units. Okay, whatever you want to go over. Okay.